Schnauzer, is that right? Schnauzer. Okay, scalable profiling for likely security bug sites. Let's get this started.
Thank you very much for the introduction. Hello everybody, welcome. I will be talking about Schnauzer, scalable profiling for likely security bug sites. So let's get started. The goal of this work is to make software more secure. Now, this obviously is a goal that we share with many here, but how we're going to accomplish this goal is that we're going to leverage the knowledge of how software is developed, tested, and exploited. Considering software tests is conducted in order to increase software quality. However, often software test, the massive software test is actually conducted to increase the software quality metric of reliability. However, we are instead going to leverage the always limited test resource to increase the software quality metric of security. And this will be accomplished by taking an enormous problem domain and pinpointing the code paths which are the code paths which harbor the bugs which are most likely to be exploited. Now, we're going to see that this is going to be a challenging task, and one important component of this task is the ability to transition to path testing. Sorry. So, the vast majority of security attacks are, in fact, enabled by software bugs, and further, often, hidden bugs only appear when sensitized by the proper path. And this is an artifact of the fact that the bugs which escape the development process are often activated by the complex interaction of objects. And so what happens is that these bugs, in fact, escape code and branch coverage. Now, consider this high-level abstraction of a known fixed security bug in the OpenSSL application. Now, there are multiple paths through this code. However, there is a single path which will sensitize the bug, and that is the path that visits both the injection site and the activation site. Now, it's important to keep in mind here that attackers themselves, knowingly or not, are trying to seek out the code paths which are not tested. Sorry. So now, path testing itself is a really challenging task. And this is due to the fact that for path explosion, where the path space of an application is exponential in the execution length of that application. Another problem is that current heavyweight testing methods like concolic testing remain very slow. And so the result of these factors is that comprehensive path coverage for test currently remains beyond reach. But all the while, attackers are still seeking to discover untested paths. And so this necessitates a new approach to achieve path testing. And for this, we propose a novel mechanism in order to pinpoint the paths where bugs are hiding that are most likely to end up being exploited. And this we call the dynamic control frontier. Now, the dynamic control frontier represents the line of demarcation between dynamically seen paths of execution and those which are unseen. Simply, it is the frontier of the path space explored by an application. Consider this simple sequence of basic blocks in execution, where the series of basic blocks, A, B, C, and D, is seen to execute. However, the series of basic blocks A, B, C, and E is not executed. This path, A, B, C, E, is a combination of an executed path and the potential continuation of that path left unexplored. And this will be the basis for our intuitive guide to achieve path-based testing. Now, the set of all such paths is the dynamic control frontier for an application. Now, what makes the dynamic control frontier valuable for path testing? Now, first, let's consider how software is tested. Now, software developers extensively test applications. In fact, in many cases, the cost of test exceeds 50% of the entire development effort for software. But again, this focus is largely on reliability. Now, at the same time, users are also extensively testing an application, in some cases much more so than the developer. But what we have is a resultant significant overlap in developer test and user execution. Now, similarly, an attacker will generally execute an application similarly to an ordinary user. However, they will provide slight permutations of input to cause slight but expected deviations from the typical control flow of ordinary users. What the dynamic control frontier is it is the intersection between heavily tested paths and untested paths, which are yet immediately reachable. Now, when we consider how to analyze for the dynamic control frontier, first consider that a single user only profiles an instance of an application. However, we are most interested in a non-trivial sized population of users, as these represent the code paths which are not tested nor executed with any real frequency by any user. And we're more interested in these paths because attackers are more interested in discovering these paths, as they are much less likely to be tested and yet remain immediately reachable. Now, in order to handle this, we propose a distributed DCF, Dynamic Control Frontier, profiling system in the user space accomplished via sampling, where the users will profile an application for Dynamic Control Frontier paths, which will be sent to the developer for analysis. Now, the developer will create a comprehensive image of the Dynamic Control Frontier for all users and identify the high confidence Dynamic Control Frontier paths with which to guide path-based testing, automated path-based testing, and that will find the latent bugs. This test coverage will then further shape the developer analysis of the Dynamic Control Frontier. Also, global path filters can then be transmitted to users in order to shape profiling as well as minimize the actual work of the end users. Now, in order to test the value of the Dynamic Control Frontier, we developed dynamic path profiling utilizing the Dynamo Rio binary instrumentation platform. And this is accomplished by sample profiling of finite length n paths determined by n conditional branches in a path. Again, where the final conditional branch is only seen to execute in a single direction. And a key insight here is that we need only instrument paths which are actively being sampled. Now consider again the previous example of the high-level representation of the known bug in OpenSSL. At some random bounded intervals, we select a path for instrumentation and we insert a few assembly instructions into the path to be sampled. Then, on the final unseen control flow decision of the path, we create a dynamic control frontier hypothesis, which is also inserted into the code. Now, this hypothesis represents the idea that this instrumented path will be in the dynamic control flow. Now, if after a long waiting period, the path, the instrumented path, in conjunction with the dynamic control frontier hypothesis are not executed, then the hypothesis is considered to be validated, and it will be added to the dynamic control frontier. If, however, in that period of time, the path tracking and dynamic control frontier hypothesis are executed, then that hypothesis is refuted. In either case, the instrumentation is then purged from the code. Now, in order to evaluate the performance of our profiling system, we selected popular network-facing applications which face an increased risk to profile, or to increased profile to attack. We further preferred applications with high-quality test suites, especially fuzz testers. And we executed these applications, profiling them for their respective test suites, collecting the application traces, which are shown in the second column. Now, to get an idea of the potential finite length n path space, in this case, for this chart, a length of 4 conditional branches, we statically analyzed the code base to determine a conservative estimate of the potential number of unique length n paths, which is shown in the third column. And lastly, we analyzed these application traces for the number of unique dynamic control frontier paths within the context of the traces, which is shown in the last column. And the important thing to notice here is that just the unbounded path space is exponential with the length of execution. And some of these, of course, run into billions of instructions. However, the number of dynamic control frontier paths for these applications range into the thousands. So since we seek to harness the power of user execution, we have to evaluate the overhead of profiling in the user space. Now, we see here variability in the amount of overhead, but the average for all benchmarks is about 2.8 times the uninstrumented execution time for an application. However, if we look at the base overhead inserted by just the DynamoRio platform itself, we can see that the essential work of dynamic control for frontier profiling itself is in fact minimal, as we can see the difference between the Dynamo Rio without any profiling instrumentation compared to the Dynamo Rio with our profiling instrumentation on the average. Now, though this overhead remains above the desired level for universal adoption in the user space for all applications, this nevertheless demonstrates that dynamic control for the essential work of dynamic control frontier profiling is yet achievable. Now, since we advocate a profiling system, we have to evaluate the ability to, in fact, discover the entirety of the dynamic control frontier for applications. Now, we looked at the application traces collected from the benchmarks in their test suites, and we modeled our sampling methodology on these traces to determine its ability to, in fact, discover 100% of the dynamic control frontier. And we see that for all applications, we do achieve 100% coverage. However, the important thing that we need to look at here is the fact that for these application traces, which ranged into the billions of instructions, we can recover the entire dynamic control frontier by sampling with trillions of instructions. And what that means is that we can do this analysis within the context of thousands of users, which is within a feasible range for many applications. Now, for the most important part, and that is, even though at this point we had not yet piped dynamic control frontier analysis into automated test, we nevertheless challenged our profiling technique to find the path locations of known security bugs. Now, the advantage of utilizing known security bugs is that we can know the precise code location of the bugs. It can be determined ahead of time what the sensitizing paths are for these bugs. We can then compare this to the known set of dynamic control frontiers for an application. And the purpose of this was to determine that if these security bugs did indeed lie within the dynamic control frontier. Now, what we discovered was that for the entirety of our benchmark applications, we had in excess of a conservative estimate of well over 100 million potential finite length end paths, unique. And of that set, there were about 80,000 dynamic control frontier paths for all benchmarks combined. And we discovered 14 known security bugs identified in the National Institute of Standards and Technology, the National Vulnerability Database, of a variety of exploit types. That we discovered these bugs, in fact, were on the dynamic control frontier for these applications. And the important part of that is that had DCF analysis been conducted, it would have given the opportunity to determine the paths for these bugs before they were exploited. Now, we conducted a similar study on the SQLite fixed bugs database as well. And what we discovered there was that 12 of the most 20 recently fixed bugs at the time indeed were on the dynamic control frontier that we discovered for that application. And further, 5 of those 12 bugs were clearly enabling security exploits. So in conclusion, we state that efficient, user-enabled dynamic control frontier profiling can expand test for software security. And this will be accomplished by identifying code paths which are harboring bugs more likely to be exploited before they're exploited. And this will make software more secure. Now going forward, we are working on a more efficient user profiling implementation system and deploying that system for a substantial application with a substantial population of users. And also, at the same time, integrating dynamic control frontier analysis to guide automated test, and with the goal of discovering new security vulnerabilities. Thank you.
Any questions?
Hi, I'm Ben Zorn from Microsoft Research.
Hello.
Hi, yeah, it's a nice talk. So I guess I have two questions. The first one is, do you know the testing techniques that were used in those applications where you found the bugs that didn't find those bugs? Do you know why they remain in the software that they were where you were able to find them, the other ones weren't?
Yes, and to be clear, we didn't do bug finding. We looked at the paths that these bugs had been found on, and then we compared those to the paths of the dynamic control frontier to see if there was an overlap. But that is, there were many different answers for that, in fact. I poured over a lot of these bugs from this national vulnerability database for many applications, just beyond the ones that we did. And there's a lot of reasons. Some of them are bugs that are injected when they do other bug fixes. So they have a cascade of bugs. Others are on programs that don't achieve branch and code coverage. But it seems like a common thread is that these are often long-running bugs that are on applications like SQLite, which has a pretty good code test database, and they're never tested. They're never caught by this test. And I say that it's because of the fact that some of these bugs are on these highly specified paths that you have to execute in order to activate the bug. And we're not yet testing these applications in all possible control flow scenarios.
Do you know if directed fuzz testing was used to test those applications?
Now, the SQLite does have fuzz testing. That's why we tried to seek out applications. Not all those applications had fuzz testing, but some of them do, and yet those bugs still escape that. So, and now, I talk about directed fuzz testing like Sage from Microsoft, right? That's the big one. That's the best. Now, that's really great. However, what's lacking there is the fact that as they try to bend branches through generations, they're trying to discover new pockets of unexecuted code. However, we're not still trying to bend all those branches in all possible directions to try to get to that code. And that's what I'm getting at here with, that's really the next step to make tests better, is to be able to do that. Comprehensive path test, but we can't.
Right.
It's too burdensome. So what we're trying to do is, we're trying to limit that to a subset, a subspace of paths that are going to be more valuable to test. So that can test that, but it's not seeking to, it's just kind of incidental if it happens to hit the correct path to a pocket of code.
Yeah, the second question I had was, had you considered using some kind of fuzz testing on the frontiers that you found in your analysis? And if you did you find any bugs?
Yes.
That would be the real, sort of.
Yeah. We've absolutely considered that, and I'm working on implementing it right now. but it turns out it's a lot more, it's actually probably the most difficult technical challenge yet facing us, because a lot of tools that we could adapt from, like CLI, part of CLI is that their selling point is that once you get to a piece of code, you don't have to figure out how to get there again, right? Which is good for their purpose of branch and code coverage, but for our purpose, it's not. So trying to get a tool together that will do the kind of thing that Sage does, but also prefer not just branch directions unexecuted, but paths, is proving to be a lot of work, which wasn't completed yet when we did this.
So is it not, are you not able to reconstruct an input that will exercise the code to the path that you have?
Yes, actually we could do that.
Yeah.
We could, by hand, figure out all, exactly what you're saying. An input that will, in fact, elicit this.
Yeah.
It would seem like doing that exact thing is just a recreation of the bug, right? I mean, if we give it the exact same inputs, I mean, a lot of these bugs in the National Vulnerability Database, depending on the application, but especially applications like T#, will give you exact inputs on how to make these bugs happen. But if we profile that, we're just going to see those paths.
I was thinking of all the other paths that didn't result in a bug, a known bug, but might actually result in a known bug, because
absolutely,
that would be interesting.
And the expectation is, and that's exactly what we're doing right now.
Okay.
And we expect to get results from that. Thank you.
Right, just one more question.
So, I mean, if you kind of looked at say the top 25, list of, vulnerabilities, and then kind of, done an analytical analysis of whether the DCF would actually work, I mean, would detect those or not. I mean, so for instance, simple buffer overflow, which is still number 3, all the paths get executed. It has to do with the size of the input. So it would seem like DCF would not apply there.
In some cases, some of the bugs we found in the National Vulnerability Databases arose from configuration errors, which are happenstance whether or not a certain control flow is going to activate or not. It's not necessarily dependent. However, the overview of the high-level bug in OpenSSL, in fact, which is a buffer overflow attack, in fact, is dependent on a specific control flow.
I'm sure you can come up with an example of one, but
yes.
They're often, it's an off by one error. Every path is executed. It's just that you went one more time through the loop. And, that wouldn't...
Right, correct. Okay. And we're not saying that this will solve all those types of bugs. The point is that the next generation that we would like to move to in test would be path coverage. However, using concolic execution, we can't really establish an entire coverage for that yet. So this will yield better results for that type of test. But it certainly will not find all potential kind of bugs, or a bug that is just entirely data dependent.
Right. So, again, I guess that's what I'm suggesting is I think it'd be interesting to kind of, categorize things so you can kind of say, yes, this would work here, no, it doesn't have any chance here. So you just kind of, like SQL injection, is that something this will cover or not? That kind of...
Yeah, that's a great point. We'll have to do that because that will further highlight just how useful this is going to be. Right? What percentage of what we're trying to really do can we do? Yeah, that's really valuable. Thank you.
All right, so that concludes our session. Let's thank the speaker again. Thanks for coming.